computer. Great. Okay. So we left off here, I think, with the hashing and the graph algorithm that we did Dijkstra's, and then there was prim. So we are now on the coding section of this part of this. So that's means I should probably do this. So, all right, all these deal with binary search trees. So we should totally do that. Close. And open up a chat window. Yeah, I need a nap too. All right, so, and we'll just toss this over here, which says, okay.
Rosen?
Yes.
Are all the these recordings on Zoom's cloud recording, or is it on your YouTube?
YouTube, but I didn't upload Mondays.
Okay, thanks.
Okay, I'll do that today. All right. So we've got exam review, we've got a static node, left, right, and E item. So we'll do that rather than key data. That's fine. No worries. Okay, so we can just use ours. So it says a binary, this class deals with binary trees. So this is the method for using recursion to search for an item, right? Given a node and a key, basically find the node that has this, although they separate key data here like it's a hash map. So it doesn't matter. But basically it says rewrite the search method so that it uses iteration rather than recursion. Okay, so that you can do that. That's no problem, although it's rather silly in my opinion, but I'll go ahead and do that. So public static E on, and we're going to look for a key. So EE. So we're going to return an E, and it's going to be a, and this method is called search, and we're going to take in a node root and a E key rather than, okay, so there we go. So now we want to search for something. I'm going to return null over here until otherwise specified, just because I like to have everything compile. All right, now let's go ahead and do, so base case should probably be the same. If root equal null, return null. Okay. Give me 1 sec. When is the exam? Good question. I'll be right back. I need to make sure that my kid's okay. I heard what you said. So laser, did you think something for it? Kid is watching Magic School Bus downstairs. So, and I told him that if he needs anything important, just come and get me. So, okay. So if root is null, then what do we want to do? If root is null, then we return null. If, so otherwise, if root isn't null, then we need to do searching, but we're not going to be using recursion. We're going to be using iteration. So we would say node current is equal to root. We'll start at the root, and basically we'll say while current is not equal to null. That probably will obviate the need for what we have. So yeah, that's going to obviate the need for the base case, because the base case only applies in recursion. So what we're going to do is we're going to say, hey, we're going to basically look at one node at a time. And as long as the node we're looking at isn't null, we should probably continue looking. And if we're done, well, we didn't find it, so return null. So while, let's see, while current is not equal to null, if current dot. So basically, first thing we want to check is current dot item dot equals. Let's change this from item to key. This from key to item. So if the item inside the node we're looking at, if that's equal to what we are looking for, let's go ahead. Actually, let's just do a compare to. And what we're going to do is I'm going to, E extends comparable E to make sure this compiles. So there we go. Int comparison is equal to item dot compare to. It's easier for me to do the item dot compare to. I'm dot compare to current dot item. So if what I am looking for, is equal to the, if what I am looking for is the item at the current node, then that's great. So if comparison equals 0, then I found the item. So return, let's go ahead and return. What do we want to return? We want to return the item in it, which is silly in this case because we're using the key value. So we can go ahead and do like, okay, I see their point. I see their point for that. So we'll just go ahead and return the node. We'll go ahead and return true instead. Make it a Boolean. Just because what they're doing is a map, more of a tree map kind of deal. I mean, how do people want me to do this? Do you want me to turn it into a Boolean statement or make it a tree map kind of deal? Do people care? Am I just shouting into the void? Return. I'll just do this because it's quicker. Return false. So if we found it, return true. So I'm going to just say, hey, is it in the tree? If we found it, return false. Otherwise, return true. While current is not equal to null, if comparison is item dot compare to item. So if we found the item, great, return true. Otherwise, we need to check, hey, is comparison less than 1? Is it to the left? In that case, we say current, rather than recursing, we're going to say current is equal to current dot left. And otherwise, if we need to go to the right, current is equal to current dot right. And we keep doing that until we get until we hit a dead end. And if we hit a dead end, we return false. There we go.
So the value of current changes.
Yes.
Kind of like it would in recursion, just we're doing it in
Manually.
terms of this while loop. That's
Yep.
kind of cool. Is there a preference to do
Recursion, unless you're
Yeah.
working in a memory constrained thing, because it's a recursive if it's a recursive data structure. If you're working in a recursive structure or the organization of something is recursive, then use recursion. It makes sense to do that. Okay, so let's go ahead and we're going to write now this one. So I like this one a whole lot. So write a Java method named mirror that takes in a reference to a root node. So here we go. Of a binary tree and creates a new tree with its own nodes as the mirror image of a tree. So we're creating a copy. That's a mirror. For example, if root is a reference node to the root on the left, then the return value of mirror root would be a reference to the root on the right. Blah. So basically, if the left is our input, this will be the output, and it's going to be a different tree, right? So we put in the tree on the left, and we're going to get a tree on the right, which is a copy. Hint, the method is much easier when you use recursion. It's almost as though trees are made for this kind of thing, or recursion is made for this, right? So recursion is, you can do it without recursion ostensibly, but why torture yourself? Public static E node. So we're going to turn this into E's because We're going to turn it into e's for ease of use. I make some really bad puns. By the way, by the way, before we get started with this problem, and have any of you read The Longest Joke in the World? Are any of you familiar with The Longest Joke in the World? I will, I might do that for our last Monday class, do a live reading of that one, because The Longest Joke in the World is about an hour long. But for those of you who want to go ahead and read it yourself, it is, you can find it at Nate the Snake. I think it's natethesnake.com. Yeah. Let me check. Make sure I'm not sending you to, yeah, Nate the Snake. Yeah, natethesnake.com. It's a considerably long joke, and I highly recommend. It's a joke told in this form of a short story. It's quite good. My wife thought it was fantastic. So there, make of that what you will. The person who has to tolerate my bad jokes every day, possibly every hour, thought it was good. So make of that what you will. All right. So there you go. I found that I found that earlier this week, and it was fantastic, and it really made my night. I spent an hour reading it out loud to my wife. It was pretty good. All right. So given left, we return right. So what we're going to do, so let's go ahead and work on base cases here, right? Base case is always easy. So first off, I'm just going to return null out of matter practice so we don't have any errors. You'll note that basically that I always return that if I'm working in an IDE that's basically actively saying you're doing something wrong, I never go forward unless I never am moving forward unless I correct everything. This is, at this point, when you're programming, you should never really have any active errors in your code. If root is equal to null, so what's the mirror image of nothingness? It too is nothingness. So return null, right? So makes sense there. All right. So what if we're not null? What if we're not null? So, right. So first off, I need to make a new node. So, node mirror, let's call it mirror root. Mirror root is equal to root new node with root dot item as the item that we're storing in it, right? So the idea here is that we want to create a new node that is a reflection of the other. We want to create, right? We need to make a copy, right? If we passed in one, we need a new one over here. Make sense? If we passed in a one on the left, we need a new one on the right. Okay. And then we're going to need to return that mirror root because that's going to be the guy that's holding up the whole chain. So now we need to figure out what to do with the left subtree and the right subtree. Okay. So let's start with the most basic thing, right? Which is that, let's go ahead and figure out, before we attach things, let's just figure them out independently before we attach them. We could probably save a couple lines by just attaching them, but let's create a mirror left and a mirror right. Right. Now, if I did, so my first instinct was basically, I'm going to walk you through my thought process, which is what I thought as I was writing this, but was immediately kind of said, no, that's wrong. So my thought process was like, okay, maybe I put root dot left, mirror left should be root dot right dot item, right? And then this should be root dot left dot item. Makes sense, right? So we look at the one here, the 2 is on the left, the 3 is on the right, and then here we've got the 3 is on the left, the 2 is on the right. Ignore the things on the bottom for now, right? Right now. But if I just attach them like and say mirror.left is equal to mirror left and mirror.right is equal to mirror right, I'm actually going to be missing all these things. So honestly, that seems like a job for recursion because, right, the entire idea is that this is all really hard stuff for my that I want my subtrees to do. So let's look at this. We've got 2, and then 2 has 4 and 5, but that switches to 5 and 4, and then their children. So, okay, so actually it's much easier than we think it is, because all we have to do now is say, hey, the mirror left is equal to, what we can do is say mirror root dot left. Yeah, let's shorten it up. Mirror root dot left and mirror root dot right. And I'm going to comment out this right now. So mirror root dot left is equal to the mirror of root dot right. And it kind of writes itself, actually, because, right, we start here with the mirror root dot right, which creates a new item. So when I call mirror on root dot right, it'll create a new copy of the right node and attach it to the left. And then it's also going to call any of the recursive mirror calls. So all I really need to do for that is this. And yeah, I'm done. Well, sorry. Left. There we go. Now I'm done. That looks done to me. Let's think about this. I pass him 1. It's going to create a copy of 1. It's going to put 3 on the left and 2 on the right. And then it's going to call it as part of calling this. Now, as part of calling 2 over here on the left, it's going to swap 4 and 5. And when we call 5, it's going to swap 6 and 7. So yeah, it works just as we would say. Why do we turn mirror root at the end? Because, well, we need to be able, well, first off, we need to attach it on lines 41 and 42. We got to attach the subtrees. And then it says, I mean, the problem states that we need to return the new root of a tree to this. So we need to return this 1 on the top at the very end. We need to return the roots. The only way we can say to attach, we use the return root to attach it, right? Over here we are, when we call mirrored right, this is what's going to attach it to the left side. All right. So let me go ahead and see what we got here. Final B. So I haven't looked at this one. Let's go ahead and see this. And so let's browse through this and I'm going to look for any interesting problems in this. All right. So is this for this class? Is it for this class? Because I don't know if it is. Yeah, 119 versus, so this looks like a lower level class. It may not actually be useful because this is object-oriented programming. Oh, hey, let's look, we've done that problem. Okay, so could be that they've swapped up the classes and stuff here. So Huffman tree. Okay. All right, so the diagram below suggests how we could implement a double-ended linked list in which we maintain a reference to both the first and last nodes in a linked list. So front, that's obviously the head and tail over here. Which of the following operations would be inefficient to carry out when there's a large number of elements in the linked list? Insertion to the end, for which insertion at the end, for which front refers, insertion at the end. None of these should be inefficient if we maintain a reference to both the first and the, oh, wait. Which of these would be inefficient? Yeah, so inserting at the front, right? We just simply create a new node. Yeah, okay, there is an inefficient one. Blame me being tired. There is a inefficient one. So, okay, let's go through this. Where pen, magic pen. Okay. Let's go ahead and annotate. Okay. So insertion at the end, right? What do I do to insert at the end? Constant time. I just simply do this. Whoop, right? Just create my node, draw my arrow, and now have this point to that, and boom, that's our head. Okay, let's go ahead and do the next one. Insertion at the end. I've got rear. So here I create a new node. I say tail.next is equal to this new node I created. And then I say tail is equal to this new node I created. Boom, done. Okay, so so both of these things. So right, inserting at both sides is fairly straightforward. Right, so inserting it, so this is basically a constant time, boom, constant time, boom. Deleting from the end, which front refers. Simply put, deleting like this, we just simply would say front is equal to front.next or head is equal to head.next. Drawing wise, all we have to do is this and go, boom, we're done. So wait, but it turns out deleting from the end is actually tricky because what do we have to do? We have to make this node the new end, right? So to delete from the end, what we have to do is we have to iterate all the way to the guy before the end. So we can say this guy is now the new end, which takes O of n time. And testing for an empty list. I mean, come on. I mean, if we want to test for an empty list, all we have to do is simply ask if front is null, so or if the head is null. And so the answer there is D. I like that one. I'll probably use it in like next future classes.
Is the answer for that one D?
Yep, D.
But if it were a doubly linked list, would they all be efficient?
Yes.
All right.
Because you can start from the end and you can get and you can go backwards and boom. You just have to go one step no matter how big the list is. So that's constant. Okay. So this method operates on a heap containing n strings. You pass in a heap. And we remove n strings. So what is the big O time complexity in terms of n? N squared. Right. So what does a remove do? A remove takes log n time. We got 5 of these suckers. So so it would be 5 times log n. So we'd have 5 times log n operations. But assuming that, right, because we'd have log n plus log n plus log n plus log n. Actually, logarithmic laws. Does that alter any way this pops up or no? I hate logarithmic laws. They're weird. Like, let's go and double check that. Right. Log addition. Ah, yes. So we could do. So what we could do like 5. This could be what? Log 5n. Point being is that as long as it's not, as long as we don't have, as long as 5 isn't n, which is probably not, we care about because what we care about with big O complexity is as n gets bigger. So it'd still be B, which is would take that many operations. So which of the following is not a topological sort of the vertices? Topological sort, we need that for the last homework. So topological sort means basically we need to start with it. Basically, we need to make sure that things go in order. So that so we can't access anything before we visited the nodes that already point to it. So anything starting with A is okay, as well as anything starting with D. That's fine. So let's go with the D first. D and then E, A. So now C, B, F, G, H. So E is perfectly fine. We're looking for one that is not a topological sort. So now let's go with, we'll start with A, and then going B, and then C. Boy, I hope I don't run out of computer ink. D, E, yep, F, G, H, yep. Okay, that makes sense. So now I'm just going to bother bubbling in the nodes now. So A, C, B, F, but here I'm pretty sure you have to bubble in D and E before we can visit F, right? It's got to have no incoming nodes. Okay, so now let's go ahead and look at, well, let's go ahead and check the others. So A, C, D, B, E, G, F, H, and then D is A, B, D, and then leave C for last. E, G, F, H, C. Yeah, so B is the answer here. This one is not a topological sort because we had this issue with B is not a topological sort because it was A, C, B, and then we went to F, but F still has two things pointing into it that haven't been visited yet. Okay, cool. Let's continue. Let's see. Oh, excellent. So the array below is to be sorted in ascending order. Okay. After the initial partition step of the version of quicksort discussed in lecture, and we'll just do ours. So how, with 36 as the pivot, how would the array be ordered? Okay. That's frustrating because for our version, 36 would not be. Okay, so how did you do this? How did you select 36 as the pivot? So typically, okay, so I don't know if you, so what, one of the efficiencies for the median, well, not the median, finding the median takes O of n, can be inefficient. Naively, it takes O of n time, but one way to do it, yeah, probably just looked at the middle. What you can do is that you can actually, but even then, all right, I'm not really sure how they chose 36 other than that, because normally you would choose 17, but that would not leave for any interesting things. So I'm just going to, just simply swap that over. Because if we did this, it would be 12. If we did a bubble, a 3-level bubble sort on these, it would come up with this. Right, and then we'd select 17 as the pivot because it's the middle item of this, but they want to select 36. So I'm not really sure which version they used in their lecture. So what I'm going to just simply do is I'm going to say is, if I were giving this as an exam, okay, this is what I would give you as your input. And I'd say, hey, do a partition with this array over here. Okay, do a partition with this array over here with 36 as the pivot, selecting the first item as the pivot. Okay, so because now why did that matter? Why in the world do I care about that? Well, because this is the wrong answer I typically get on a final exam. And it's a very wrong answer, where basically students go, 36, so put 36 in the middle for the partition, and 17, 53, 71, 62, 46, 41, 23, 12. And let's just throw in the commas there. And we're done. That is wrong. That is not the way partition works. Partition works by going going up for the first item. Sorry, that's bigger, and then looking down for the first item that is smaller, and then swapping them if they haven't passed. So what we're going to see basically is that we'd have 36, 53, 71, 62, 17, 46, 41, 23, and 12. Okay. So what I can do is that I'm going to just simply set, so we look up for the first item that is smaller. Sorry, first look up for the first item that's bigger than the pivot. Found one. Look, and starting at the back and going down, we look for the first item that's smaller. Excellent. So we found them. So now we swap them. 53 and 12 will be getting swapped. So 12 and 53. All right, now we look up for the first item that's bigger. And now we look for the second first item that's bigger. Boom, boom, found one. Look down for the first item that's smaller, found one. Okay, and now we swap them if we haven't crossed yet. So 23, now 71. Now let's go ahead and look up for the first item that's bigger. This rather is a convenient one. First item that's bigger is going to be, boom, 36. First item that's bigger than 36. Now let's look for the first item that's smaller than 36. Not this one, not this one, not this one, not this one. Found an item that's smaller than 36. Boom. Now we swap them. So that was 17 and 62. Okay, and now erase. 1 second. I need to add a reminder. Okay. And so we swap them, and now we're going to go ahead and look up. Yeah. So now we've got that. Now we're going to go ahead and look up for the first one and down, sorry, first thing that's bigger, and down for the first thing that's smaller. And so since they crossed, since up and down kind of crossed their paths, we know we're done. We've partitioned the array successfully into all the things that are smaller and all the things that are bigger than the pivot. And so now we go ahead and we swap it with the last thing in this subarray. So now this would be, so our answer would be 62, 12. Sorry, not that one. We'd swap it with this over here. So we'd swap it with 17. So our answer would be 17, 12, 23, 36, 62, 46, 41, 71, 53. Okay. So again, watch the videos if you're confused about that, again, on the way insertion sort works. So I'll use the array as written for the next one, which is, and for all the other ones, I'm just going to do them below Radic Sort. So for the initial iteration of Radic Sort, how would the array be ordered? Now, Radic Sort, did we go over Radic Sort or no? I don't think I do a video on that one. Did I do a video of this one? Oh, Radic Sort is amazing. It is an amazing, bet now's a great time to go over Radic Sort anyway. Okay, so Radic Sort is a, Radic Sort has an amazing runtime. It is, I think it's OWD, sorry, I think it's OWN runtime, if I'm correct, or maybe it's, what is it? Yeah, Radic Sort. So it's completely different because Oh yeah, it's WN. I got it right. Okay, so just want to make sure I was using the right term. I can't remember it's D or WN, where W is the word size. Although word size is weird because we're dealing with numbers here. But in this case, that's 2 because they're 2-digit numbers. So what in the world is Radix Sort? Well, all the other sorting algorithms are real, right, that we've done. They rely off of figuring out where do we move things based off of comparing things. Okay. We have to compare things in order to find out where they go, right? Like if we're doing bubble sort, which we check, hey, 17 versus 53, 53 versus 71, 71 versus 62. Which one of these, right? We say are any individual pair out of order for bubble sort? Make sense? We're comparing 2 items to see if they swap. Radic Sort is completely different beast because unlike all the other sorting algorithms we have learned so far, it is non-comparative. It does never compares any number to any other number. Instead, it sorts using the most unexpected of all things. It sorts using queues. What? Queues, you say? That's impossible. How in the world do you sort using a queue? A queue is just a thing you throw things into if you want things in order. Wait, in an order. Ooh, that seems relevant. Order, right? Different type of order, maybe? Let's think about this for a second. Okay. So what we do for Radic Sort is pretty simple. You take basically you do for Radic Sort, what we're going to do is basically so basically when we're sorting anything like numbers or strings, they have quote unquote digits. And in this case, right, we've got 2-digit numbers, right? Or if you're sorting words, maybe we're sorting words, you basically your biggest word would be the W. So if you were if hello was the longest word in the bunch of words you were sorting, then W would be 5. That just simply tells you how many iterations of this we're going to do. But as far as queues are concerned, we make 1 queue for every possible value of a digit. So for our 10-letter words, sorry, for our decimal numbers, we are going to be making 10 queues, 1 for each digit. Oh, sorry, 1 for each value. 0, 1, 2, 3, 4, 5, 6, 7. I don't know. Math gets hard at some point, and then you forget all the basics. All right, so these are a bunch of queues that I've just created here, listed from 0. Wait, I made 1 extra than I needed because, of course, I did. Right, 0 to 9, all the possible values. If we were doing letters instead, we'd have 26 different values if they were all lowercase, A to Z. So as you can see, it's kind of space inefficient like that, but that's okay. The queues are fine. And so what we do is that we look at the least significant digit and throw each of them into a queue. So for instance, 17, I'm going to throw that into the 7 queue. 53, I'm going to throw into the 3 queue. 71, I'm going to throw into the 1 queue. 62, I'm going to throw into the 2 queue. 36, I'm going to throw into the 6 queue because, again, we're looking at the least significant digit, the 1's place. 46, I'm going to throw into the 6 queue, so 36, 46. 41, I'm going to throw into the 1's queue. 23, I'm going to throw into the 3 queue. And 12, I'm going to throw into the 2 queue. Okay, and now that we're gone through our array, we are now going to rearrange the array by basically going through in order of the digits and dequeuing everything. By the way, if I had a 3-digit number over here, if these were 3-digit numbers, like 1003, then for the purposes of the algorithm, I just throw a 0 in front of everything here. Make sense? Similarly, if I had a single digit number over here, I'd just call it 09 and I'd throw it over here in that queue. But anyway, now you basically just prepend in zeros to make everything the same length. Okay. So now what am I going to do? So I've gone through everything. They're all in queues. So now all I'm going to do is I'm going to go out and dequeue everything. So 71, 41, right? 62, 12, 53, 23, 46, sorry, 36, 46. 36, then 46, because that's the order they went into the queue, 36, 46, and then 17. And you're like, okay. And by the way, this is this over here, assuming they did least significant digit first, which is the correct way to do it, in my opinion. You can go most significant digit first. But assuming they did it the way that I did it, and this would be and the way I teach it's obviously the correct way to do it, then this is the answer that we were looking for. This would be the answer for B. But you're like, okay, but it's not sorted. How in the world does this help us? Well, it's only the first iteration. So let's go and finish. Let's go ahead and finish up doing all this other stuff so that we can, let's do this again. So with Radic Sort, what was going on? We did, so with Radic Sort, what we did is that now, if you look, everything is sorted according to the ones place, which is pretty interesting, right? So now what we're going to do is we're going to toss these in based on the tens place. So 71 is going to go into, so we did the ones place. Now we're going to do the tens place. So 71 gets thrown into the 7 cube, 41 gets thrown into the 4 cube, 62 gets thrown into the 6 cube, 12 gets thrown into the 1 cube, right? Because again, now we're going with the tens place. 52 gets thrown over here, 23 gets thrown over here, 36 gets thrown over here, 46 gets thrown over here, and 17 gets thrown over here. And now we go ahead and erase everything up here because we don't need it any longer. And now we just dequeue. So what do we do when we dequeue? We are just going to go ahead and dequeue everything in order. 12, 17, 23, 36, 41, 46, 52, 62, 71. Awesome. Boom. We are done. And we did it by never actually comparing one number to another number, which is great if you're like working with mechanical machines and don't have access to actual computers. Like this IBM card sorter. It sorted a large set of punch cards using Radic Sort. So it's pretty cool. Now, why don't we use this? After all, it says WN, right? That seems better than log n. Well, it could be, but let's think about this for a second. First off, okay. Let's just consider for a second how it works with actual computers, though, right? Suppose we're sorting integers. Well, and what are integers in what are integers in Python? No, sorry, Java. They are 32-bit numbers. Let's go ahead and leave the positive negative discussion, which has the same effect, for another day, and just assume they're unsigned. So only 0 to a very large positive number, like 4 billion-ish, right? So, okay, so they are 32-bit, meaning they're 32-digit numbers of zeros and ones. So we're going to be dealing with 2 queues, zeros and ones. And so how many iterations do we have to go through to sort integers? If these are 32-digit numbers. How many iterations will it take? Answer? Well, it took 2 for 2 digits. So, yep, 32. It's going to go 32 iterations. So the runtime we would say is 32n. Right? So now something like merge sort takes n times log n, which I'm going to go ahead and rewrite these to compare each other. So this is n times 32. So versus something like merge sort, which will take n times log n. So the question is, which is better? Well, so Radic Sort is going to be better when 32 is greater than, when 32 is, when 32 is less than log base 2 of n. Okay. So the question is, when is that going to be the case? When is 32 going to be less than log base 2 of n? So let's think. Well, when would they be equal? Log base 2, they'd be equal when we would put 2 to 32 in there. It's actually basically as easy as the math for logarithms get, fortunately. So they'd be equal when basically it was 2 to the 32. So when we're sorting more than when we're sorting more than 4 billion-ish integers, then Radic Sort is better. But also it has a memory cost because of those queues. So there is something like that to keep in mind. All right. So, but for most cases, we're not sorting 4 billion. So, you know, stuff like Tim sort and merge sort is still better. Bubble sort and selection sort don't really need to. Probably not. Radic Sort has special cases when you want to use it. Okay. Let's say you need to sort a collection of data that is stored in a singly linked list. Would shell sort be a good algorithm to adapt to this problem? So shell sort is a version of insertion sort, but it does. So insertion sort would normally be perfectly fine if it was a sum. No. So first off, it's a version of insertion sort. And insertion sort is so first off, doing insertion sort the way we've learned it in class is terrible on a singly linked list. For it to go on a singly linked list, you'd want it to go in reverse, where basically where you bubble up the biggest, you want to bubble up each item to the end, except it doesn't really work like that for insertion. Any kind of insertion sort seemed like a terrible idea for a singly linked list, right? Because let's think about that for a singly linked list. Right, 5, 10, 3, 7, 2. Right, so if it's like this, 5, check the next one. Okay, that's okay. 5, check this one. Now we have to move this one over here and compare, and then we have to compare this one, which involves using a lot of get operations, which seems like a terrible idea for a singly linked list. If it was doubly linked, we could just go and iterate through it back and forth, no problem. But that seems terrible. And since shell sort is just basically the last step of shell sort is to do an insertion sort, yeah, that's pretty terrible. Also, shell sort would have to furthermore, shell sort would be even worse, since basically you have to traverse not random elements, but like elements defined by a certain gap through the list, and then insertion sort those, and you'd have to jump around. And anything where you're jumping around in a singly linked list or even a doubly linked list is terrible. And so there's my answer. What would be a good thing for a singly linked list to do? Probably merge sort. Merge sort is, I mean, because anytime we're breaking anything apart seems like a good idea. And you can fit, but working as a singly linked list is, you know, well, since you're going to be copying it over anyway for a singly linked list, you know, you just break it in half, which takes O of n time. And then recombining those takes n log n time. So yeah, that'd be fine. So here's some Java code. Figure out that stuff. No, thank you. Don't need to. Header index returns the index, takes in two array integers and turns the index of the first occurrence of the first list in the second, or a negative one. If so, basically what we're looking index of 1, 2, 3, 1, 3, 6. So I guess we're looking for this over here. So that's actually a fairly straightforward problem, but I'm not going to end. It's actually like one of those common problems where if you know some special algorithms, you can do that, but I don't need, say, tree. We've done this one already, did that one. Do we have any new coding problems? Recursive backtracking, the knapsack problem. Ugh. But it's good to look at. Okay, so wait, it's packing. He really went all out on there. So I'll come back to this one to discuss it, because that one is something you'll discuss in algorithms. If you take that one, I want to see what else they do. Suppose you want to print a binary tree like the one shown below in reverse level order. So the labels of the tree in the diagram would appear in reverse alphabetical order. You may use the stack, queue, or other auxiliary data structures. Describe an algorithm that would accomplish the task. Okay, so we do breadth first search, right? A, B, C, D, E, F, G. Put each of the answers into a stack rather than putting it into a string. And since it's in the stack, we'll get in the order that we do it, right? It's breadth first search, but rather than putting our output into a string, we just put it into a stack, or put it into a string anyway, then reverse the string. But it says use a stack or a queue. So whatever. So let's see. Two variables, head.next, circle the box, was expression of it. Adds to the end of a circle. Here, write a static method with the header. Ooh, I like this one. Node.append head character C. So it appends a node containing character CH. So that would just be E element here. To the end of a singly linked list, the first node of which is by parameter head. A value of head null should represent the empty list. So the nodes are instances of the nodes from the previous page. So basically it's saying, hey, you've got a linked list here. Here's a method, given the head of a list, add it to the end of a linked list. And it's outside. So there's no tail. So you should use iteration, but it should work regardless of the length of the initial list. So basically it's saying you don't have a get, you just have the next. So we should return the reference of the first node. Okay. Yeah, this is, so it says you should use iteration, even though recursion is actually the easier way to do it. So I'll do it both ways. So I'm going to go ahead and use the node here that we already have. I'm just not going to just going to go and be dumb and add this. Okay, makes sense. I'm just basically that way I can refer to it as a node in this document as well. Okay, it's horrible programming, but whatever. It's an interesting problem and I'm going to take it. So there we go. And we're going to change this to E item. And we're going to basically be taking right static E node, E append this node. So this is actually better to do recursive. So basically all we're doing is adding this item to the end of the linked list, right? So what we want to do is basically say, hey, oh, and the method should return the head of the linked list. So what's cool now, the reason I mentioned that this is easier with recursion is because linked lists are recursive data structures, right? Here, let me show you. Boom, boom, boom. boom. I think I probably went through this in my videos, but right, here's my head, right? But this node over here, right? He's actually the head of his own linked list. So that actually gives us a recursive way of thinking about data structure. So each node you can consider the head of like a sublist. This makes it actually fairly straightforward. So first off, right, what if my head is null? If head equals null, then, so this is how you would do it recursively, which they said not to do, which they said you got to do it iteratively. But I want to show you this way because this is the easier way, I feel. So if the head is equal to null, then return new node and it says you need to return the head of the new list. So it would be the new node item like this. Boom, we're done with that. So if it's not empty though, then what do we do? Well, the problem got, well, if it's recursive, we just simply say, well, if head.next equals null, that's kind of another base case. I know what to do in that case. If my next face is null, right? If I pass you the head of a list, right, and we're asking to add it to the end of the list, then it's pretty simple for it to figure out, hey, I just need to attach it and return myself. But actually, we can simplify that process even further by just doing this. Head.next is equal to append. So there's two ways. There's a couple ways to do recursively, and this is the way that's short and kind of hilarious. Append head dot next item. Boom. There you go. That's all you have to do. But in a more expressive way to do that, we can just do we can add in another condition and just simply say, if head if head.next is null, this is probably the way that makes more sense in the way most of you would code it. If head is equal to null, recursively, I mean. So if head.next is equal to null, then that's fairly easy. What are we going to do? We're going to simply say, hey, head.next should be equal to a new node, right? If I've got an empty space, that means that space is the tail. So that space would be the tail. So just create a new node and attach it there. And then we're going to return our head because it says, hey, says basically that after appending it, it should return a reference to the first node, which is this guy, me. Oh, and then finally, else. Head. Let's go and take a look at this one. Head.next equal. Okay, so what if basically though we do head.next is not null, right? What if head.next is not null? What do we do in this case? In this case, well, then we just simply say, hey, we do the same thing we wrote before, which is simply say, hey, that's your problem now, and I'll go ahead and return myself. Same thing, you can actually just kind of remove this step, it's extraneous. All right, so how do you do it iteratively though? It's very similar to how we did the other problem with the binary search tree, where we're just going to use a current. So we say node E current is equal to head, and then we say while current is not, let's see, not equal to null. Actually, I probably would still use this case, this base case, just for simplicity's sake. So while current, so I don't have to think about it. While current is not equal to null, what am I going to do? I'm going to say, hey, while current is not equal to null, what am I going to do? I'm going to say, hey, do I have an empty space? If current dot next is empty, add the item on. That's what I need to do. So if current dot next is empty, add the item on. Current dot next is current, and then we would want to change that condition. But basically, we keep going, and so current dot next is equal to new node. Okay. And then with the condition we'd want to break it out, because otherwise we'd continually keep adding, because we'd move on to the next one, and that wouldn't have, we'd just added a node, so we'd move on to the next one. But anyway, we could just, because what we need to do here is say current is equal to current dot next to continue moving on. And I'll put in else to make it more explicit, even though it's unnecessary. The else is kind of implied there. So we could do that. Another way we could do it is just do a done loop, because this will never actually fire. So while done, so Boolean is equal to done. Boolean done is equal to false. While not done, let's say done, true, and then we don't have to do that whole breaking thing, which is kind of frowned upon sometimes, but I'm pretty sure this is even more frowned upon. But whatever, that's how it works. Oh, except that we have to return head at the end. Okay, if you want to improve the efficiency of the append method, what additional information would we need to maintain about the linked list? The tail. And then it becomes, then it goes from an O of n method to a constant time. Because if you know where the tail is, you can just append it to the tail in a set number of steps, no matter how big it is. Whereas we have to iterate through n nodes here. Okay, search, mirror. Oh, what is the big O implementation of mirror? That's a great question. The mirror question we wrote earlier. Well, since it touches every single node in the list, it's O of n. There you go. Node in the tree. So now I'm going to read out the Knapsack problem to you, so so you can work on it, because it's interesting. It's worth looking at. But it's one that's very popular in algorithms. The idea behind a knapsack problem is fairly simple. You're a burglar, right? And you got yourself a knapsack or a backpack, right? And you break into a safe, and before you is all this loot, right? You got, so, or maybe you're a treasure, or maybe you're an adventurer. You just slew this dragon, right? And you know, you just slew this dragon, and before you is the dragon's hoard, and you've got a backpack, but your backpack only holds so much, right? Your backpack can only hold so much weight, right? So that's the amount of loot you can probably carry out before somebody else comes in and steals the rest and takes the rest of the treasure. So you want first pickings here, right? You've got the dragon hoard, you've got your backpack, your knapsack, as it's called, because it's a knapsack problem, and you've got all this treasure. Now, treasure isn't always things. Sometimes it's like currency, right? That, like in the safe, that's fairly reasonable bills and stuff. But sometimes it's not. Sometimes it's like priceless paintings or gems, which are super lightweight, but they, you know, they are worth a lot of money, right? Right. So the idea behind the knapsack problem is to maximize your gains of loot. In other words, pack in as much weight as you can, pack in as much value as you can within the constraints of the weight. So basically, knapsack problem is a classic problem that can be solved using recursive backtracking. You're given a set of items with different weights, And you need to pack some subset of the items into a knapsack that has a specified total weight known to the target. A solution is given to a problem called packing. So, okay, there's a couple different ways of doing this. So the weight, I think there's a different way of doing it. Where you're trying to maximum. Here, we're just trying to fill up the, okay, but for this problem, here, we're just trying to say how much stuff can we fill up with the weight? Forget about value. We're just trying to take the heaviest stuff out. Okay, so suppose, I guess lead is very valuable in this context. Okay, so here we've got a 15, an 8, a 5, and a 4. So here's an illustration of how recursive backpacking could gives the knapsack a total weight of 17 pounds. So 5 plus, right, but okay, specified weight known to target. Doesn't give me the target though. Okay, so basically it says, okay, so they're saying here, your backpack only holds 17 pounds. Try your best to fill it up. So what we could do is that we could look at 15. We could try to put 15 in, and it does because we have 17. Now, 17 minus 15 is 2. So now we want to try packing additional items into this backpack. And we check, we can't do 15 and 8. Too much. 15, 5 is more than 2, 4 is more than 2, so we can't fit it in. So we move on to the next item. So 8 is less than 17, so we put that in, and then we move targets. So 8, 5, 4 is a solution that would get there. So it wants you to basically try to solve this problem. It's a very interesting problem. It's one you'll get experienced in with your data structures. Sorry, with data structures. I don't know why I misremembered it as like value. I think, is that a variation? Or was I just making stuff up? Right, knapsack problem. All right, no, I was right. So here, which would maximize the value of money while keeping the weight under or equal to 15 kilograms. Here, basically, in this simplified version, which is perfectly fine for a final exam, basically they were saying, hey, we're going to just for the sake of ease consider weight and value being equal in this case, right? So suppose you had giant chunks of gold, giant bars of gold, right? So the heavier the item, the more it's valuable. So you want to try to maximize how much you can carry. As you can see, actually, maximizing the value, something's actually a very important problem. You know, you can see like, oh, that I can see some context for that. I mean, maybe we don't all slay dragons at times, but it has been, let's see, studied for more than a century, dating back to 1897. 0, 1, bounded knapsack, unbounded, and decision problem in the form of knapsack is NP complete. There is no known algorithm that is both correct and fast in polynomial time in all cases. So the decision problem is NP complete. The optimization is not. So basically, there's no known polynomial algorithm that can tell, given a solution, whether it is optimal. So pseudonomial, so it is a tough problem, but it's not one that can be done really fast, but it's an interesting problem and one worth looking at, and not one that I can solve in 5 minutes for you guys and give you an adequate solution, but it's worth looking at for that one if you want to try a challenge for that one. Now, for other exams that we'll be going over, you'll note that basically this is an algorithm that I have linked for algorithms and data structures from Uppsala University. Algorithm data structure. So notice that basically it goes into more detail about, like, you've got big O of n, big O, mega of n, and theta of n, which is things that we really haven't tackled in this class. That's okay. Some places like separate out stuff with object-oriented programming and data structures, and then you have data structures and algorithms. It really depends on basically the curriculum. It's all the same stuff. It's just sometimes split differently between the classes. Like here, though, this is a perfectly good problem, which I think we'll end on. So let's consider insertion sort and merge sort. For each algorithm, what would be the worst case asymptotic upper bound on the runtime if you know additionally that A, B, and C? All right. So basically saying what's the big worst case big O if you know about information. In sorted, reverse sorted, and is just all n items are the same number. So let's talk about insertion sort. Actually, let's talk about merge sort. Merge sort's easy. What is the average run case for merge sort? N log n. What's the worst case runtime for merge sort? N log n. What's the best case runtime for merge sort? Does merge sort ever vary based on what you give it? There you go. That's your answer. Merge sort ABC, it's all n log n, no matter what. Boom. Merge sort's done. That was an easy one. Give me like, what was that? My 7.5 points, please. All right. So let's look at insertion sort. Insertion sort's great. If everything is already sorted for insertion sort, it takes O of n time because basically you go through each item and you try to push it back into there and you say, hey, I can't move this item because the thing before it is smaller, or doesn't exist in the case of the very first item. So if it's already sorted, basically you'll check each item once, O of n time, boom. If it's reverse sorted, that's actually the very worst case scenario for insertion sort because first time we won't have to move, but the second item we'll have to move one item to make it like, so say we've got 100 items, it'll be 100, 99, 98, 97, right? So first item would be 100, then it would be 99, 100, and then we'd have 98, 8 after that, then would be 98, 99, 100, and then we'd have to move the next item over 3 times, 97, 98, 99, 100. So basically be 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 all the way up, right? That is n squared. So sorry, that's 1 to n. The summation of that is that comes out to O of n squared, right? Actually, reverse sorted is the very worst thing you can do for an insertion sort. That's like the unoptimal case. If it's n copies of the same number, that's the same as being already sorted. Boom. All right. Now it's got some theoretical. So why did I put on this exam? Was it just because of that one? No, we can look at this one, this tree problem, as well as this hash table problem, as well as this hash table problem. I really like this one. And then I won't be able to accept demos today, unfortunately, because I have a contractor coming. And then we have this binary search tree one. Then we have this one, which has a couple interesting problems. My first link had a really good problem, unfortunately, that just doesn't exist Although this one has a lot of those good a bunch of those scenario questions, which I guarantee will be on the final exam. Like, give me the best data structure for this scenario. So that's a good one to do. Some more graph problems on this exam. And again, we're going to go over these exams more. Do I have a PDF for this? No, I don't have that one anymore, but I do remember the question that I find the most interesting, which is given a list of users and their log time, give me the average log time for each user, which is a map problem. So we'll be working on that. But anyway, I have a contractor coming soon. So it was good seeing you all today. I can't take demos, but thank you for coming by and listen to me drone on in a way that will be advantageous for you in the future.